Hi Abby. I'm going to hold up the homework. It was a new paper we got, 5.2, and I'm going to hold that up and you can write down some of the problems. There are 12 problems that we started on in class today. They're show that's that I taught about on Wednesday night's video. So that's what we began to work on as soon as we got into the classroom today. So I think most people got a couple, like five or six out of the 12. So if you would take note of them, give a couple of them a try. I did 2 of them almost all the way on the video, previous part 1. So this part 2 is just for you, Abby. So hope you're up to seeing this, and eventually you will be. So I have this paper for you, and actually Miss Tammy has one if somebody had time to run by and get your work, but if not, then you can use what I put on the camera here in a minute, or just pick it up tomorrow. So you're not too far behind. I would just show it to you now. So hang on to your seat. You're gonna whirl the camera around. All right. All right, I'm going to show you this side first. You'll see number 6, 7, 8, 9, 14. Let me roll down. 15, 17. Roll up. Oops, there's little 12 over there. I forgot him. All right, so that's the ones on that side of the page. And down here is number 21. Now going over to the other side, 23, 26, and 27. All right. Okay, just so you can get a head start on those, you can pause the video and see how that works. Let me get it set back up on our screen. Oh, that's close enough, I guess. Let me tilt it a wee bit. I wanted to talk to you, Abby, just a moment about what we did in physics. I forgot to turn it on when I was doing the teaching part, because first we worked on the vanilla review problems, and we were up through number 28, I believe. So then after that, I went on into teaching new things, and I forgot to turn the video on. So I thought I'd just tack on a brief discussion with you of what went on in physics. So here's what I'd like you to look at as far as physics goes. There are all kinds of energies, and these are 1, 2, 3, 4, 5, 6. 6 energies. Let me see if I'm recording. Yeah. There's 6 energies that we have listed. And it turns out the ones that we were studying, where we had the boulder up here, and that was showing potential energy, and then when it fell, some of that potential energy became kinetic energy. And then at the bottom, just before it hit, all of the kinetic energy, it all became kinetic energy. Well, it turns out that all of these forms of energy have potential and kinetic energies. So mechanical has a potential and kinetic, chemical, electrical. There's only one of these that has just kinetic, and that is heat. So heat does not have a phase where it can be stored, where all of these other ones can be stored in some way. And so this has kinetic energy only, while the other forms of energy that we talked about have both forms that are kinetic and potential. What's interesting, do you know which form of energy that this is when the boulder rolls off of the cliff? It's actually mechanical energy, which I always thought was odd because there's no machine involved. But mechanical means anything that's moving. So a lot of things are mechanical energy, which you might not think they are. So the reason I brought that up with all those forms of energy, if you could write those down in your comp book or on a paper to go in your comp book, that will help you. The reason I brought this up is because these energies, according to the first law of thermodynamics, it says energy cannot be created or destroyed. So energies, instead of popping up where they never were before, are just transformed from one type of energy to another. So it seems sometimes that they come out of nowhere, but they've always been transformed from some other form of energy. So we talked an example where a man pushed a car and he gave kinetic energy in the form of mechanical energy, which is moving. He gave mechanical energy to the car and it moved. Where did he get his energy? Well, it turns out he got his energy, or he was able to push the car because of his muscles. And his muscles received their energy from the food that was eaten. And where did the food get the energy? The food got the energy from the minerals in the ground and the sun. So you can see that all the energies come from some other form of energy and are not created or destroyed. They just change forms. So we kind of use that concept to launch into two problems. I did one and then I set up the second one, but the bell rang. So if I could show you the one and set up the second, you'll be right on par with where we are if you're able to watch this before returning. So the picture that I want to show you is of a car, and that car is being pushed. The car is being pushed with a force, and it creates a kinetic energy when it moves of 0.46 joules. And the car itself is 230 grams. I'll go ahead and change that to kilograms, because we never use grams. How fast is the car moving when friction has done 0.30 joules of work? How fast is the car moving when friction has done 3.0 joules of work? I'm sorry, 0.30 joules of work. All right. So I noticed that to answer the question how fast, it's a velocity question. The only velocity that shows up in any of our formulas is kinetic energy equals 1/2 mv squared. So the question will always lead you to the right starting point. So what do I put in? Obviously I know mass from this number. I'm looking for velocity, so I can complete the problem if I know kinetic energy. Well, this energy was given as 0.46, but once I push the car, it starts with the initial kinetic energy, but then it slows. And it is friction that is taking that energy. So the energy is transferred from kinetic, that's the moving car, and it's robbed by the force of friction, and at that point it becomes heat. As you can see, when you rub anything together, you'll feel heat. Just those few swipes and I can feel the heat in my hands. So this kinetic energy is transferring to heat energy when the friction is applied. So kinetic energy started at 0.46, but then friction came along and opposed it and did 0.30 joules of work. So we're going to subtract that from this to see how much of the work that was initially, how much energy initially was given to the car remains. So that's going to be the new kinetic energy. So when we subtract 0.30 from 0.46, we get 0.16 equals 1/2 mass times velocity squared. So the only thing we had to realize that we couldn't use this number because friction had robbed it of this much energy. We had to subtract the two before we could use this equation. When someone tapped that out at school, they got 1.2 meters per second, which is a slow velocity, but makes sense when you're playing around with a small toy car. Alright, the next one that I didn't get all the way through was a car, small car again, 1, 2, 3, 4 kilograms. And that car is moving 6.1, actually that's a real car, it's not a toy, 6.1 kilograms, and then it's going to come to a stop. And the frictional coefficient is 0.45. And the question is, find the work done by friction. Find the work done by friction. And again, I look at the question to know where to start. And it says find the work. So we looked in the beginning of our comp books and we saw that work is force parallel times distance. And that is where we stopped. So I just wanted to give you an idea of what you missed in physics, and it is an abbreviated class for you, but it's just so you can understand what we jump back into tomorrow if you're able to come, and hope you are. See you then, hopefully. Bye-bye.